Okay, so in this lecture, we will in this lecture and the next actually we will show a lower bound on the a streaming lower bound. Okay, so I suppose we have seen this basic streaming model in the lecture by Dr. Karthik. So the model is that a stream of elements comes is arriving one by one, and you have very limited memory, so you cannot afford to store the entire data as it is, but you can store some. You can choose to use the limited space that you have in whatever way you can. So let's say you have some limited space, and then the stream of elements, let's say they come from the set 1 2 3 up to n, and let's say there are m such objects that are appearing again and again. So m such x1 x2 up to xm, m for Mumbai. So x1 could be any one of these, x2 could be any one of these, etc. So one extreme case would be that all of them are equal to 1, right? Or it could be that 1 2 3 4 5 6 7 8 up to n, 1 2 3 4 up to n, and so on, right? It just that everything keeps repeating, right? So the number of distinct elements that appear is called f0, the zeroth frequency moment. So that's the number of distinct elements that appear. So in the case where all of them are equal to 1, f0 is also equal to 1. In the case where all of them are equal to 2, even then f0 is equal to 1, right? Because only one distinct element appears. If all the elements appear, then f0 is equal to n, right? You may recall the frequency moments f1, which is just the sum of the frequency that 1 appears and 2 appears and 3 appears, which will actually be equal to n. f2 will be the square of the number of times that 1 appears plus square of the number of times 2 appears, and so on. f3 will be cube of the number of times this appears, and so on, and so on. And we also remember f infinity, which is the maximum number of times that any of these quantities appear, right? So that's the f infinity norm. Okay, so this theorem, I suppose Karthik stated this theorem in some form. In a data stream, both f0 and f2. So again, I stated the definitions of other frequency moments, but f0 is the number of distinct elements that appear. Right? Both f0 and f2 can be approximated within a factor of 1 plus or minus epsilon, with probability 1 minus delta. So epsilon is the leeway that is being given for the approximation, and delta is a probability in which you can make an error. And this can be done in space 1 over epsilon square log n plus log m times log 1 over delta. So notice that epsilon, when you want a better approximation, the space requirement increases. And when you want a better error, that is delta is small, then again the space requirement increases. But better approximation seems more expensive than better accuracy, right? Because here it is 1 by epsilon square, here it is log of 1 by delta. So the question that we will look at is this 1 by epsilon square really necessary? Right? Can we do something? Can we get away from this? And the answer is no, it cannot. It is essential, and that is what we will show in this lecture. Actually, so this was a result by Indick and Woodruff. I have their names written here. Indick and Woodruff from sometime like 2004, 2005. So they showed that this 1 by epsilon squared factor is essential. So what we will actually show in this today's lecture and the next lecture, is that for a 1 plus or minus, so where epsilon is equal to 1 divided by square root n. So when epsilon is 1 divided by square root n, the approximation is 1 plus or minus 1 divided by square root n. Such an approximation requires linear space. So when epsilon is 1 by square root n, then 1 by epsilon square is n, right? So we will show that in the case when epsilon is 1 by square root n, it requires linear space, which is actually equal to 1 by epsilon squared space. And the statement that I just said, that 1 by epsilon square factor is essential, is not true when epsilon is much smaller than 1 by square root n, because you can always estimate this in a linear space. So when epsilon is much smaller than 1 by square root n, that means we don't need more than linear space. But if epsilon is at least 1 by square root n, then we need this factor, right? And we show it in the extreme case when epsilon is equal to 1 by square root n. And the proof, in fact, it is true for the epsilons above 1 by square root n also. These proofs also can be inferred from this without much difficulty, but I won't go into that in this lecture. So this also implies that 1 by epsilon squared bound for epsilon greater than 1 by square root. So what we will show is 1 by epsilon squared factor 1 by square root n approximation requires linear space. Again, this is not true when epsilon is smaller than 1 by square root n, but it is true for epsilon greater than 1 by square root n, although we won't do both. Okay, so we will use a reduction. So how will we show that it requires linear space? We will show a reduction from a hard problem in communication complexity. So you may recall from the lecture of Karthik sir how communication complexity leads to streaming lower bounds. So one standard problem that we have been looking at throughout this course has been disjointness. So let us see if disjointness can work. So let us say this is X, Alice's input, this is Y, Bob's input, and let's say this is an instance of disjointness. Right? So obviously this is not disjoint because first X1 is equal to Y1 equal to 1. Right? But anyway, the point is not for this specific example. But if it's an yes instance, meaning if the inputs are disjoint, so what is F0? So think of these strings as, you can think of them as 1 followed by 3, 4, 5 followed by 8. And this is 1 followed by 4 followed by 7. So you can think of it as a sequence 1, 3, 4, 5, 8, and this is 1, 4, 7. Right? You can think of it as this sequence. So now disjointness makes sense. And you can also think of it as a stream where 1 appears, followed by 3 appears, followed by 4 appears, followed by 5, followed by 8, followed by again 1, 4, and 7. So now you can ask what is the frequency moment, the zeroth moment of this. Or in other words, how many distinct elements appear. Right? So disjointness wise, these are not disjoint. How many distinct elements appear? So 1, 3, 4, 5, 8. 1, so that is 5. 1 has already appeared, 4 has already appeared, 7. So that is 7 has not appeared, so that's a new element. So 5 here plus 1 additional new element, so 6 is a total number of new elements if you consider X and Y together in a string. So what Alice and Bob can possibly do, right, is to Alice to do something and then send the information to Bob, and then Bob can continue processing. So together X and Y together can be considered as one string, right? And Alice, and if there is a X and Y together can be considered one string. And if you have a protocol for disjointness using less communication, and if somehow disjointness relates to the zeroth moment, then that would imply that zeroth moment is also hard. Because, so what I want to say is, if you can compute frequency moment, and from that if you can compute disjointness, then that would imply that frequency moment is hard, because we know disjointness is hard. So there is no way you should be able to compute disjointness in less than linear communication. So frequency moment also will require linear communication. But this doesn't work out. Why? Because suppose it's a yes instance of disjointness, then the frequency moment of the entire stream is, so yes instance meaning it is disjoint. So x and y don't share anything. But then the frequency moment is none of the elements that appear in x reappear again in y. So the frequency moment is the size of x plus size of y, right? Number of ones in x plus number of ones in y. If it's a no instance, then it could be, it will not be number of ones in x plus number of ones in y, but it will be lesser than that. But it cannot be the smaller than size of x or size of y. So f0 lies in between size of x plus size of y minus 1. It is at most that, and at least max of size of x or size of y. Okay. So this is what we know. So just to take slightly more concrete example, let size of x and size of y be n over 2. Then the frequency moment, the number of distinct elements is n if and only if x and y are disjoint. And if they are not disjoint, let's say x and y are not disjoint, then f0 could be as high as n minus 1, right? Because they could overlap in just one element, they will still not be disjoint, but together they span n minus 1 elements. So when they're disjoint, they span n elements. When they're not disjoint, they could span as much as n minus 1 elements. Now the ratio of n and n minus 1 is very small, but it is like 1, n by n minus 1 is like 1 plus or minus 1 by n, right? But what we are trying to show is a 1 plus or minus 1 by square root n approximation. That's what we are interested in of f0. So such an approximation may not be able to distinguish between n and n minus 1, because these are closer than 1 plus or minus square root n approximation. This is 1 plus or minus 1 by n apart. So such an approximation will not be able to separate n and n minus 1. Hence, disjointness doesn't work out. We need to find another problem. So what we will find out, what we will use is another problem called gap Hamming problem. So we have already discussed Hamming distance. So given x and y, the Hamming distance of x and y is the number of bit positions where x and y differ, right? Number of bit positions where they don't agree. So what is gap Hamming in problem? Gap Hamming problem, there is a subscript c here of x and y. It's a promise problem. So what's a promise problem? Promise problem means that we know certain promises are given and we need to solve the problem only with while respecting, if the problem respects those promises. So what is the promise given here? We know that the Hamming distance between x and y is at either less than n by 2 minus c square root n or more than n by 2 plus c square root n, right? So the Hamming distance, let's say n by 2 is there are n bit inputs, so let's say take n by 2, so either it's somewhat c square root n smaller than n by 2 or even smaller than that, or significant c square root n more than n by 2 and more than that. So the cases are separated. There is a gap in between that. These are not exhaustive, right? You could have x and y where the Hamming distance is exactly n by 2, but we are told that such cases won't occur. So given such a problem with such a promise, we want to answer 1 if the Hamming distance is lower and 0 if the Hamming distance is higher. And what if the actual Hamming distance falls in between? Then we don't care what the protocol outputs, right? So that's fine. So with this promise, we need to solve the problem. So it kind of makes the problem a bit easier than solving the original problem. So what we will see in this lecture is that if the one round gap Hamming problem requires linear number of bits, linear omega n bits, then approximating f0 within 1 plus or minus square root n requires linear space. Okay. So what we will see today is that if this requires omega n bits, then approximating also requires omega n space. And to complete the proof of the fact that approximating f0 requires linear space, we also need to show that gap hamming requires linear bits, but that we will see in the next lecture. And notice that the C here I have written as 4. Okay, this doesn't look much like a 4, but I want C to be equal to 4. Okay, fine. So we will, assuming gap hamming requires linear complexity, we'll show that F0 requires linear space. Okay, and this is in the one round communication complexity setting and randomized setting. Okay, let me just see. Okay, right. So what is the template of the proof? Suppose there is a little of n space algorithm for, so it's a reduction from gap hamming to f0. So if gap hamming is possible, it's a reduction from gap hamming to f0. So that means if f0 is possible, we will convert it to a protocol for gap hamming. Suppose there is a sublinear space algorithm for f0, right? So now Alice, so in the streaming algorithm, we are considering Alice's input, the Bob's input, as a continuation of Alice's input. So Alice does whatever processing she wants to do, and then it's a sublinear space algorithm. So Alice can send whatever is the state of that sublinear space algorithm to Bob, right? So the space that Alice is using is sublinear. So whatever space she is using to store her intermediate state, that she will send to Bob. And then that is the only communication that Alice does to Bob. And after that, Bob continues from where Alice left off. Right? So it doesn't matter whether Bob is computing or Alice is computing, because whatever Alice was doing was, she had a limited memory, and that limited memory has now been transferred to Bob. So Bob can continue from exactly where Alice left off, just as Alice would have done. And Bob computes a 1 plus or minus square root an approximation to f0, and this f0, this approximation to f0 gets a so this approximation to f0 gets a protocol for gap hamming problem, and the entire all throughout the only communication is just a one round communication, right? And that happened from Alice to Bob, which was the space requirement of this f0 algorithm. So which is a little o of n, which means this is also little o of n, which is contradicting. We will see later that gap hamming requires linear bits. Okay, so why is this going to be true? So let Sx and Sy denote the set of non-zero integers of x and y respectively. So this is exactly what I said earlier. So if this is x, Sx would be 1, 3, 4, 5, 8, and Sy will be 1, 4, and 7. Right? These sets. Right? So these are the set of non-zero indices. So what is the f0 here? F0 is the number of distinct elements, and we will use t to denote that, okay, because writing t is simpler. This is the size of the union of the sets. In the previous example, it was 5 plus 1, 6. Right? F0 is the size of the union. What is the Hamming distance? Hamming distance, so let's say this line denotes x, this line denotes y, and this dotted lines denote zeros, and these dotted lines denote zeros and y. Right? These are the ones in x, these are the ones in y. So Sx union Sy is this entire set. Intersection is the part where they overlap. So the Hamming distance is this part plus this part. So the union minus the overlap is the Hamming distance. So the union is t, minus the overlap is the Hamming distance. But you can also write t, which is a union, using the standard set theory thinks that union is equal to size of x, size of sx plus size of sy minus the common portion. This is the principle of inclusion exclusion. Size of x plus size of y minus the intersection. Now, when you combine this, you get that when you substitute this value of sx intersection sy, you take from here and you substitute over here, you get that the Hamming distance is equal to 2t minus sx minus sy. So what we are going to try to do is that can we somehow, so t is a frequency moment, right, zeroth moment. Can we somehow use the zeroth moment to infer something about the Hamming distance? So now we have a relation between them, but we still are working in the realm of approximation. So we need to make sure that even with the approximation, if we get the value of t, we will be able to get the value of the Hamming distance, right? And we have certain error parameters, and that has to be respected, right? So this idea we need to formalize. So suppose Alice, so now notice that this also requires the knowledge of sx and sy. Bob knows t, Bob will know t at the end of the computation, but Bob will not know sx. But no problem, sx Alice's is the size of Alice's set, not Alice's set itself. Alice can send the size of the set in log n bits, at most log n bits, right? Or log n bits. And we are talking about the lower bound. The lower bound that we are talking about is linear lower bound. So adding a log n won't change the lower bound. So we can assume that Alice sends the size. Okay. So in addition to the state of the algorithm, whatever her space whatever was stored in her space, she will also send the size of her input. Then Bob can do whatever calculation and arrive at an possible estimate of the Hamming distance. Okay, so we'll do it a bit differently, and then Bob can say whether he's in this case where the Hamming distance is less than n by 2 to minus square root n, c square root n, or greater than n by 2 plus c square root n. The first case, then the answer is 1. Second case, the answer is 0. So suppose now Bob is able to complete the execution of the algorithm and get an estimated t. So the estimate is called t tilde. So all that we know is that this is an approximation algorithm. So t tilde will be between 1 plus or minus epsilon, 1 plus or minus 1 by square root n of t. So which means t tilde will be at least 1 by square root n times t, and at most 1 plus 1 by square root n times t. Okay, now there are two cases. The first case is when the Hamming distance is greater than n by 2 plus c square root n, right? Now, okay, we computed this. The Hamming distance is equal to 2t minus sx minus sy. So which gives us that t is half of Hamming distance plus size of sx plus size of sy. We know that Hamming distance is at least this, so we write that, plus size of xx plus size of sy divided by 2, this half. Right? So now rearranging terms, I get sx plus sy is at most 2 times t minus n by 4 minus c by 2 square root n. Again, same things. Now we know that t is less than or equal to, so using the first inequality, t is less than or equal to t tilde divided by 1 minus 1 by square root n. So t is less than or equal to t tilde divided by this, because recall Bob does not know t exactly, he only knows an estimate of t, right? So t is at most this minus the rest of the things are the same, and we call this quantity as L of t tilde. It's a function of t tilde, so we call it L of t tilde. So in the case when the Hamming distance is at least n by 2 plus c square root n, the size of sx plus sy is at most L of t tilde. In the other case, when the Hamming distance is at most n by 2 minus c square root n, you can do the same calculations again. You get this, and you get greater than or equal to here. So we have to replace t by a equivalent greater than or equal to inequality. So t is greater than or equal to t tilde divided by 1 plus 1 by square root n. So we get this inequality. Sx plus sy is greater than or equal to 2 times t tilde divided by 1 plus 1 by square root n minus n by 4 plus c by 2 square root n. The plus appears here because of the difference in the cases. So these are the two inequalities, Sx plus Sy. In the case of case 1, it's Sx plus Sy is at most this quantity which we call Lt tilde. Case 2, it is Sx plus Sy is at least this quantity which we call U of t tilde. Okay. So now, what is it again? Just to recall this situation, Alice starts the estimation of f0 and Alice transfers the control to Bob. So she sends also the state of the algorithm. So suppose the state of the algorithm was sublinear. She sends that sublinear piece of information. She also sends the size of Sx, which is also sublinear, right? Which is log n. Now Bob estimates t, and that is estimates t means he computes a value of t tilde by completing the f0 algorithm, f0 estimation algorithm. Right? Recall, we are trying to reduce gap having distance to f0. So assuming an algorithm exists for f0, we are trying to compute gap having distance. So Bob estimates this, and then he checks whether Sx plus Sy is at most L of t tilde or Sx plus Sy is at least U of t tilde. Right? And based on this, he classifies whether case 1 or case 2. And case 1 or case 2 is actually the answer, right? Case 1 means the Hamming distance is the function value is 0. This means the function value is 1 as per our definition. Right? Less means less Hamming distance is 1, more Hamming distance is 0. So that's all that Bob has to compute. He has to just say whether it is in case 1 or case 2. And this helps him compute the function. Now, to be able for Bob to be able to make these judgments, it would be essential, right? We don't want both of these things to be satisfied, right? So as of now, we don't know what is L of t tilde and U of t tilde. Let's say L of t tilde was, this is an example. Let's say it was 70. And U of t tilde was 60, then Sx plus Sy could be 65, and both of these are true, right? So that is not good. So we want to make sure the values of L of t tilde and U of t tilde are appropriately computed. So what we want is for this L of t tilde to be smaller than U of t tilde, so that only one of these cases happen. Right? In the case of case 1, this happens. In the case of case 2, this happens, and not that. So we ideally want something like L of t tilde to be smaller value and U of t tilde to be larger value. So let us see. So in other words, we want U of t tilde minus L of t tilde to be a positive quantity. If it's a positive quantity, then there is no way that both of these things can happen together. Right? So now let us check what is U of t tilde minus L of t tilde. So let's see. Now this minus n by 4, so both of them are written similarly. So minus n by 4 cancels. Plus c by 2 square root n minus c by 2 square root n, that gets double. And t tilde divided by 1 plus square root n and minus t tilde divided by 1 minus 1 by square root n. So that will write. So I'm just writing the same thing here. So I'm ignoring the middle term. So 2 t tilde into 1 plus 1 by 2 t tilde into 1 divided by 1 plus 1 by square root n minus 1 divided by 1 minus 1 by square root n plus 2c times square root n. Right? So c by 2 is c, and there's a 2 outside. 2c times square root n. Right? And now if you simplify this entire thing, you already have this 2c square root n. If you simplify this entire thing, you will get 2, sorry, you will get 2 square root n divided by n minus 1, I think. Inside the square bracket, you will get 2 square root n divided by n minus 1. And this, you can take the square root n outside, and you can bring in the 2t tilde, and you can simplify this. This is just arithmetic. You can just verify this. And we know that t tilde is at most n, because t tilde is the estimate. So it estimate of the frequency moment, and the number of distinct elements cannot be bigger than n. So any meaningful estimate will be at most n. So because t tilde has a minus sign here, so we need to take an upper bound for the inequality to work out fine. So this is at least 2c minus 4n divided by n minus 1 times square root. So now we want this quantity to be positive, and we see that when c is equal to 4, we have 8 minus this quantity here, and when n is, let's say, 3, at least 3, then we have 4, this is 3 by 2, so 4 times 3 by 2 is 6. So this quantity is positive when c equal to 4 and n is at least 3, right? So now Bob can tell whether he's in case 1 or case 2, and hence he can say whether the function, the gap Hamming function, is 0 or 1. And that completes the proof of the reduction from gap Hamming distance to the computation of f0. And what so I will summarize the proof again. So the key thing about the proof is, first of all, we are showing that a 1 plus or minus 1 by square root n approximation requires linear space. Okay? It's a reduction from gap Hamming. It's a reduction from gap Hamming problem to f0. Meaning, if there is an algorithm for f0, how can we compute gap Hamming? So the key thing is both Alice and Bob can treat it in two different ways. They can treat x and y as their own inputs for the gap Hamming problem, and they are also going to be treating it as a continuous input for the screening problem for the f0 estimation. Now, if we can find an estimate for the f0 for this entire thing, then we want to say that we will be able to get a meaningful estimate of the gap Hamming problem. Right? So that's the goal. So what is it? How can we get a meaningful estimate? So, or what is the template of the algorithm? So Alice starts executing the f0 algorithm, transfers the contents of her space. Suppose if there is a sublinear space algorithm, she transfers the sublinear space. She also transfers the size of her input, right? The number of ones in her input, which can be done in sublinear space as well. Now Bob can compute a 1 plus or minus 1 by square root an approximation to f0, and this leads us to a correct computation of the gap Hamming problem, right? Gap Hamming function. And why do these relations exist? This is because f0, which is the frequency moment, is the size of the union Sx, union Sy, right, denoted here, and the Hamming distance is t minus the intersection, but t also can be written as size of Sx plus size of Sy minus size of the intersection. So we can get this relation between the gap Hamming, the Hamming distance, and the twice the Hamming distance and the frequency moment. So now, given an estimate of the frequency moment, so notice that Bob will not have an actual value for t, he will have an estimate, which we will call t tilde. Can he exactly determine which side of the gap Hamming instance he is going to be? Right? So So we need to make sure that even with the error in the estimation of t, he will correctly identify which side of the gap Hamming instance he is going to. Right? And that is what is going to be done here. So let's say there was a t tilde and estimate that Bob computes. So t tilde will be between t times 1 minus 1 by square root n and t times 1 plus 1 by square root n. And Bob has to distinguish between these two cases. The Hamming distance is less than n by 2 minus c square root n or greater than n by 2 plus c square root n. So let's say it is the first case, greater than n by 2 plus c square root n. Now t satisfies this, and the Hamming distance has this lower bound. So we can get sx plus sy is at most t tilde divided by 1 minus square root n, 1 by square root n, minus n by 4 minus c by 2 square root n, and which we call to be lt tilde. And in the other case, you get a similar inequality, sx plus sy is at least 2 times t tilde divided by 1 plus 1 by square root n, minus n by 4 plus c by 2 square root n, which we call ut tilde. And now we are going to show that ut tilde is greater than lt tilde. Hence, Bob can compute lt tilde and ut tilde and also compute sx plus sy and then determine whether sx plus sy is going to be less than lt tilde or greater than ut tilde. It cannot be in between both because we know we are given the promise that the Hamming distance is either less than this or greater than this. We are in case 1 or case 2, not in any other case. Right? So just to now, final thing to verify is that ut tilde is at least lt tilde, and that is easy by just subtracting lt tilde from ut tilde. You get this, and which can be simplified to this. So t tilde is at most n, so we get this. So when we have c equal to 4 and n is at least 3, we get that this is a strictly positive quantity. Hence, Bob can distinguish the two cases. So if, again, just to summarize, if there is a sublinear space algorithm for f0, that gives us a sublinear space algorithm for gap Hamming, randomized algorithm, because the statement that we want to show is that there is no sublinear space algorithm that computes this within an error. So if there is a sublinear space algorithm, that will also be a space randomized algorithm, that will also be sublinear complexity randomized protocol for gap Hamming. So now what remains to show is that there is no one round. So and notice that the protocol for gap Hamming that was created due to this reduction was a one round protocol, because Alice sends Bob something and then Bob computes. That's it. There is no back and forth. Right? Just Alice sending Bob something. What we want to show to complete the proof of approximating, complete the proof that F0 requires linear space, is to show that a randomized protocol, randomized one round protocol for gap Hamming, right, that requires a linear number of bits. Right? A randomized one round protocol for gap Hamming requires linear many bits. So in fact, I thought the lecture could be too long if I try to do that proof, and that's why I didn't do the latter proof. So, but however, I prepared the notes, so which I will complete in the next lecture. So I prepared the notes. So from the midway page 5, you can go through the notes, and independent, like together, if I put both of them together, maybe they make for a heavy lecture. So, but independently, they are kind of easy lectures, I think. So, if you're interested, you can go through this proof as well. But anyway, I will record a separate video for this and share that. All right. Thank you.